Good day everyone, I'm Shara Nicole Bordeas from BSECE4 and today I'll be presenting our first laboratory activity in ELX 402 which focuses on designing a point-to-point path profile in microwave communication. A microwave link is a point-to-point communication system that transmits data, voice, or video signals through microwave radio waves between two fixed locations. So, it is like talking with invisible beams. Imagine you have two walkie-talkies that need to talk to each other, but they are very far apart, like from one town to another. It typically operates between 1 GHz and 30 GHz. It enables high-speed and reliable wireless communication over long distances. Instead of using wires, they send signals through the air using a very fast waves called microwaves. These waves travel in straight line just like a flashlight beam. But because the earth is round and there are mountains and trees in the way, we need to make sure nothing blocks the signal. So engineers check the land and measure the heights to make sure that two antennas can see each other. Though you can also put a repeater between the transmitter and the receiver. The objective of this laboratory is to design a point-to-point path profile in microwave communication. The materials and equipment that I use in this laboratory is first Google Earth Pro for selecting the transmitter and receiver sites. Second, files about path profile for providing the procedures. Third, Microsoft Excel for computation. So this is the procedure on how I designed my path profile. I began by using Google Earth Pro to choose two suitable sites, the transmitter in Santo Domingo, Nabua and the receiver in San Nicolas, Iriga City, with a total distance of 10.7 kilometers. Before finalizing, I checked the zoning ordinance. After confirming that the setup was compliant, I generated the path and elevation profile using Google Earth Pro. In the next slides, I will show the needed computation on how to design a path profile. The K-curve explains how radio waves slightly bend as they travel through the atmosphere. This bending effect happens due to air density and temperature changes, known as the K-factor, typically 4/3, to account for this bending. By adjusting for the K-curve, we ensure that the line of sight between antennas is accurate and that the signal won't be blocked by the terrain. Earth bulge is essential. Think of the Earth like a giant ball. If you try to shine a flashlight from one side of the ball to the other, the curved shapes gets in the way. It's the same with antennas. They need to send signals to each other, but because the Earth is round, the middle part of the Earth sticks up, like a little hill. If the antennas are too short, the signal can block by the Earth's curve. So engineers use earth bulbs to figure out how high the antennas need to be so the signal can travel clearly without hitting the curved Earth. The earth bulge formula is D1 times D2 over 12.75 times K. The Fresnel radius is like an invisible tunnel around the line connecting two antennas that send signals to each other. Imagine you are shining a flashlight straight at your friend far away. That beam of light spreads out a little, right? The Fresnel zone is like that spread out area around the signal path. If something like a tree or building gets inside that invisible tunnel, the signal can bounce, weaken, or get blurry, just like hitting an obstacle. So, the Fresnel radius tells engineers how big that invisible tunnel should be kept to make sure that the signal travels smoothly. The formula for Fresnel radius is 17.3 times the square root of D1 times D2 over frequency times distance. Fresnel clearance is the minimum space that must be kept clear around the line of sight path of a microwave signal to prevent interference or signal loss. Fresnel clearance is like the safe space that needs to stay empty around the invisible signal tunnel between two antennas. Imagine you are throwing a ball to your friend. If there are trees or poles near the path of the ball, it might bump into them or slow down. The same thing happens to microwave signals. Even if the antennas can see each other, stuff that's too close can still mess up the signal. The formula for Fresnel clearance is 0.6 times F1. The Earth's curvature means that our planet is round, not flat. Because of that, when two antennas are far apart, the curved ground in the middle can block the signal between them, kind of like a small hill getting in the way. Imagine two kids standing far away from each other trying to see over a ball. If the ball is big, they can't see each other unless they stand on something taller. That's what happens with antennas. So engineers calculate how high the antennas need to be, using the Earth's curve and the height of the ground or the elevation, to make sure the signal can travel smoothly over the curve and not get blocked. So this is the computation on how I designed my path profile. And lastly, we add 15 meters because trees grow, buildings may be built, and the land is not perfectly flat. The signal needs extra space so nothing blocks it.